In this video, two of my colleagues are featured to share an example workflow for automated welding program development. They'll begin in Siemens NX with a SMIT bracket that highlights weldment callouts. Next, they'll move through a full workflow of robot programming, inspection, and finally comparison between the original CAD model and the final part. Let's get started.
Hi, I'm Chris Miller, Application Engineer here at CCAT.
Hi, I'm Maleeha Wahid. I'm a software developer here at CCAT.
And today we are going to walk you through an automatic welding workflow using model-based definition and the power of digital thread. Okay, great. Let's hop right into it. So as you can see here, we have a SMIT bracket that has been designed within NX. We have a lot of PMI callouts here that are associated with the geometry and features. If I zoom in a little bit, we can see that we have some weldment callouts as well.
So what's the best method to put the weld callouts?
Yeah, that's actually a really good question. And for this workflow, the best method and really the only method is to create these welds as a solid body. To best show that, I can go ahead and hide the main brackets and just show the weld bodies. I will go ahead and also remove some of this extra PMI that we don't need to see at the moment and just focus on the weld bodies. So as you can see here, we have some continuous welds and we have some intermittent welds. For example, we have this 8 measured fillet weld that's 50 in length with 100 millimeter in segments. Likewise, we have the same over here. For us to continue this workflow, we have an application ribbon up here that we want to go into so we can activate MBD Connect for NX. Once I click that, it's going to create another tab on our ribbon. I'm going to enter that to utilize some of the functionality. And the main function here is to export our QIF. I will go ahead and just save that right here, let it process. And while it's processing, it's going through all the different views and capturing all the PMI that's associated with each feature, each geometry, and the views that has been enlisted within.
So you started with the Siemens native file and now you're exporting it in a QIF format. So what information about the welds does that file contains?
Yeah, the QIF is going to be able to contain all the metadata that's associated with the weld bodies so that it can be used downstream in order to produce the automatic welding program using the visual component software.
Okay.
So with that being said, we're going to go ahead and jump on over into our MBDVidia software. The first thing I'm going to want to do is to bring in that QIF that I just created using the MBD Connect function within NX. Here we can see the weld bodies that are associated with the SMIT bracket. The other features, the brackets themselves, are being hidden at the moment. We could display those if we'd like. For now, I will go ahead and just also show all the annotations. Let's remove these and just show the welds. Now the callouts are also associated with a bubble number. So MBDVidia takes the information that's being provided through the design phase, adding PMI, and will automatically create the bubble numbers or the key characteristic numbers that are associated with the part. So now that MBDVidia has gone through its process of redefining all the weld information, I will go ahead and save this file so that we can continue to use it later downstream. So I'm going to overwrite that. Okay, great. The next thing we want to do is now hop on over into our visual components. Visual components is a software that's primarily used for manufacturing sites in order to do simulation and automation. In this case, we're going to use it to automatically program our robot to create those welds.
So I see that you started with a visual robotic system already set up. Is that necessary?
Absolutely, yeah. So what we want to do is we want to simulate our manufacturing environment. That way the program can use the kinematics of the environment in order to create that program for us.
Okay.
Great. So as you can see, we have our virtual environment set up in visual components. The next thing for us to do is to bring in that CAD model, fix it to the 2-axis positioner, and begin our programming. So I will do that by going into the Program tab. I need to select the robot that will be doing the programming. So I will select this one here, click on our import function, and choose our CAD file. Now, after I click import, it takes a couple minutes to pull in all that data. And as you can see here, it pulled it in, and just a matter of positioning it onto the 2-axis positioner. So in order to do that, I will click on our move function. I will just simply slide it along some of its axes here, rotate the part 90 degrees about the x-axis, and finish off with aligning the bottom of our part to the top of our positioner. And that's just using the align function. So now just to finish it off, I will go ahead and move this right above the positioner and a little little bit more. Great, this should be good. Now, just to clear things up a little bit, I'm going to remove some of these callouts. These callouts were included with the part file that we imported in. For visual purposes, these are not needed, so I will just simply delete them for now. Now, just because I deleted all those callouts does not mean that the software will not know how to create the program for the welds. In fact, we're going to follow another process in a moment here where we import the QIF that we created before that contains all that metadata for the weldments and use that for the programming of the welding. In order for me to do that, I will click on the robot that's going to do the welding and the part that's going to receive the welding and import. Using the templates here, I will use import QIF welds and bring in that QIF that we created before in MBDVidia. So this will take a few moments to process. Now that I've imported the QIF welds, I will go ahead and zoom into the part and we can start to see some of the paths that the robot will be taking to create these welds.
So after the generation of the program, is it fully ready to run?
Not quite. This software will get you, roughly 80% of the programming done, so it definitely saves you a lot of time. What we would want to do is just go through the simulation of this and just make sure there's no unwanted collisions. Normally we would be able to see those or be highlighted in red if a collision were to happen. Otherwise, we might want to take a best practice that we've learned at our site that is a better method to create this weld body. So there are some cleanup touches that you might want to make, but for the most part, this is ready to go.
Interesting.
Now that we have the final touches added to our program, I think we're ready to go ahead and simulate the program. Just to point out, Visual Components works with Fronius, a solution provider for welding. They have what is called a perfect weld, and some of those technologies, including wire sense and seam tracking, are incorporated within this program. What I will do is click play here and zoom in some. Now, as we can see here, the wire tip is approaching the plate. What it's doing is just making contact with the plate, both the base plate and this vertical plate, and it will do so on both sides. What that effectively does is let the software know where the start point is and where the end point is. So if you have any clamping compensation or any defects in your part, it knows where that path should be. Additionally, if you needed some overlap welds, it has the capability of understanding where that gap is or how high that gap is, so it can compensate how fast and how much feed it's going to give. That way it's always producing a perfect weld. And if I continue to zoom in, we can see the red starting to show. This is the physical weld in the simulation environment. So as the simulation is running, we can clearly see how model-based definition workflow is really benefiting this process. We were able to simply take in our model, position it to our environment, bring in that QIF that had all the weld body metadata, and simply just begin running the program after making a few cleanups. Me as a programmer, this can save me hours and hours of time and quite frankly remove quite a few headaches along the way. Things like collision detection and avoidance is a huge help. And simply that I don't have to sit there and create every single step along the way. We can pre-default some of the settings, so we have approach angles, speeds and feeds that are also included. In conjunction with Fronius, we're able to use their solution in order to create that perfect weld. So if there's any misalignment in the real world, the real environment, Fronius will compensate for that, so we're guaranteed a good part once it's complete. So now that we have our program created within Visual Components, the next thing we want to do is to send that off, export the file, the program file, and use that to have the part manufactured.
Awesome.
Now that we've received the part back from Fronius, it's time for us to inspect the part. Today we will be using M3DI along with AO software. As you can see, there's a blue light fringe pattern being projected onto the part. As the light bends, the software can calculate this to understand what the real shape is in a 3D environment. As you can see, the robot is taking different positions along with the positioner rotating so that it can capture all angles of the part. As the software continues to scan the part, it will begin to align itself to previous scans. In the end, we will have one mesh file that can later then be exported as an STL that can then be used within PolyWorks environment. So now that we have the part manufactured and inspected, the next thing for us is to bring it into PolyWorks to see how well the part was created. To do that, I already have my part brought in, so I have the Smith towing bracket, Rev4.
I see that's a QIF extension file. Is that the same file from earlier?
It is the same file from earlier. So that's the beauty of the model-based definition workflow or the digital thread workflow, is that you just need one file that can continue along all your software. And in fact, the manufacturer for this part is all the way halfway across the country. We send this one file to them, They can use the software to generate the program, or we can send the program to them, and that's all there is to it. There's not, communication between parameters or practices. It's all contained within that file.
Awesome.
So now I will go ahead and import our scan data using this right here, this STL. Open that up and confirm that it's in the units of millimeters. Great. Now that we have our scan complete, we have imported it into PolyWorks along with our CAD. That way we can do the comparison. So the first thing I need to do is to align it. I will use the best fit approach for this one. Allow PolyWorks to process it, and we can see that it is aligned. Really the last thing for us to do is just run through the automatic reporting of it. So I will select all these faces and run the welding measurement routine. We will give it a moment to process. It's now comparing all the weld bodies to the CAD data.
So what's it's doing while it's processing?
Yeah, it's taking all that QIF metadata and using it to determine what to inspect. So a few things like the fillet, the size of it, the length of it, if it's continuous or not. It's computing all of that, and on top of that, it's allowing me to not have to enter the information, so there's no risk of a typo or user error. We are comparing it against the scan data, and we will now be able to see how well we did. So if I switch over to Control Reviewer, I can see all my results and see that we did a good job. Everything passed.
So earlier in the MBDVidia, you mentioned about the inspection report. Can that same report be used in PolyWorks?
Yeah, absolutely. In fact, I'd want to take that MBDVidia report, export it out of there, and import it here into PolyWorks. That way I have the format that I'm looking for. I have all the characteristics or the bubbles associated with the features and all the results listed into that one format. As you've just seen, we started off with a file that contained PMI, a model-based definition file, native CAD file. We've imported it into MBDVidia to create a QIF that can be used downstream in order to create this program that welds these brackets onto each other. The benefit of that is it's going to not only reduce errors from the programmer or technician standpoint, but you're also going to save time from having to type in typos and allowing the software to do a lot of the programming automatically for you. Thank you for joining us today to allow us to show you a demonstration of how model-based definition workflow can benefit your company. I'm Chris here at CCAT.
I'm Maleeha. Thank you for watching.